Hello everyone, this is Achinta Medhi, and if you have not watched the previous videos, links are given in the description below. So let's start this video. Let's discuss about kinetics of complex reactions. In complex reaction, it involves more than one steps. Okay, through those all steps, the reaction gives the product. So there are three categories. First one, first one is reversible reaction. Reversible reaction. Okay. Next, second one is consecutive reaction. And the third one is chain reaction. Now discuss about kinetics of reversible reaction. So let us consider a reversible reaction. Suppose Na NB. So in this case, this is Na to Nb. This pathway is called forward direction, and this Nb to Na, this one, okay, this path is called backward direction. So in reversible direction, there is a forward direction and there is a backward direction. So we will write here as k1 and k minus 1. So k1 is the rate constant for forward direction and k minus 1 is for the backward direction, rate constant. Okay, so in reversible reaction, if the rate of the forward reaction is much more higher than the rate of the backward reaction, then this kind of reaction will act as straight or one step reaction. Okay, when at the starting there will be a mole of reactant and here it will be 0 at the starting. So when time is t, here it will be a minus x and it will be x. Okay, so here k1 is the, let's write it, k1 and k inverse are rate constant for forward and backward reaction respectively. So we can write rate of forward reaction is equal to rate for the it will be rate constant. You have to write rate constant k1 for the forward reaction multiplied by concentration of reactant a minus x, here it will be n, as there is number of reactant molecule is n, so you have to write here n. And for the backward reaction, you have to write the rate constant for backward reaction and multiplied by at time t it will be x, and as number of product molecule is n, sorry, here it will be m, let's m, so it will be m. Okay, so the net rate of reaction or formation of this reversible reaction, it will be dx by dt is equal to, you have to subtract this one backward reaction, for forward reaction minus backward reaction. Okay, so forward reaction is this one, n minus k minus 1 x to the power m. Okay, so this is the net rate of formation or reaction. So in equilibrium condition, at equilibrium, the rate of forward reaction and rate of backward reaction is equal to each other. Okay, so at that point, equilibrium state, that means this part, this is the rate of forward reaction, and this is rate of backward reaction. So these two are equal. So if these two are equal, then this dx dt will be 0. So we can write, or in terms in case of x, at equilibrium we will write x is equal to xe. Okay, so at that point, at equilibrium, k1 a minus xe, I will write xe at equilibrium, minus k minus 1 xe whole to the power m is equal to 0. dx dt is equal to 0. So we can write k minus 1 is equal to k1 a minus xe whole to the power n, and here it will be xe whole to the power m. Substituting value of k minus 1 in equation 1. And here it is x to the power m. We can write dx by dt is equal to k1 by x e to the power m. I will take this as common as k1 by x e to the power m. So here it will be a minus x whole to the power n x e to the power m. Okay, minus, and here it will be a minus x e whole to the power n, and here it is x to the power m. Okay, and this is equation number 3. Now let's consider a simple reaction where number of reactant molecule is 1 and number of product molecule is also 1. So if we consider A, this is forward reaction, this is backward reaction, and here it is the product. Okay, so rate constant is k1 and k minus 1. In simple reaction, this equation will be reduced. How it will be reduced? You can see that dx by dt. Okay, so in this case, this n, this power n, this power m, and nm, this all nm will be disappeared. Only here is only 1 and 1. We can write k1, and this m will not be here. Here it will be only 1. We can write xe. So a minus x into next minus a minus xe into x. Okay, it will be cancelled out, only k1 by xe, and this will be sorry, here it is a, so we can take it a as common, a x minus xe. Okay, so we can simplify it. We can write it a k1 xe x minus xe. Now I will bring that x part to here, this side, dx by x minus xe, and remaining part will be here. So a k1 by xe dt, because x can only differentiate or integrate x part, x only, not this xe. Xe is different. So when you integrate this equation, it will give you ln xe by x minus xe is equal to a k1 by xe t. Okay, so from this equation we can write k1 is equal to xe by a t ln xe by x minus xe. So this is the general equation for a simple reversible reaction where only one reactant molecule and one product molecule. Now from this equation, as we have already discussed, so in this equation we will consider this k1 by a xe is equal to k2. K2 is randomly considering it, dx by dt. I am writing this is k2 xe minus x. Okay, so here k2 is equal to k1 by a xe. Okay, and from the equation, as I have already discussed, the general equation for a simple reversible reaction, which is k is equal to xe by a t ln xe by xe minus x. Okay, so from this equation we can write what a k1 by xe is equal to, here it will be only t ln xe by xe minus x. So as I have already written here, k1a by xe is equal to k2. So I will write here k2 is equal to 1 by t ln xe by xe minus x. Consider this is equation 1. Okay, so as we know that for a simple reversible reaction we can write like this reaction, k1 k minus 1, here it will be a minus x and it will be x at time t. Okay, so from this reversible reaction we can write what, k1 and reactant, concentration of reactant is equal to when it is equilibrium state. Okay, at equilibrium we can write k1 a minus xe is equal to k minus 1, that means rate constant for backward reaction, and it is xe. Okay, so we will write here k minus 1 k1 is equal to, that means k1 is coming here and xe is coming here. Okay, a minus xe and it is xe. Next I will write k1, this k1 will come here as a I am adding this k1 to k minus 1 k1. This is a mathematical theorem, so here it will be also xe will come here as a, I am adding this and this is xe. Next it will be cancel out, and here it will be only k minus 1, and k1 is equal to k1 will come here a k1 by xe, which is equal to, we have also already considered it as a k2. Okay, so as we know that k2 is equal to this much. Okay, so we can write k minus 1 plus k1 is equal to k2 means this one, 1 by t ln xe by xe minus x. Okay, so through this equation you can see that the reaction will behave like a first order reaction, with this k minus 1 plus k1 will act as a rate constant for first order reaction. This is a equation of, you can see that k1 is equal to 1 by t ln a by a minus x. Now let's discuss for reversible reaction, when both opposing processes, that means both opposing process means forward reaction and backward reaction, both processes are second order. That means there will be two reactant molecule and two product molecule. Okay, a plus b, c plus d. So here it will be rate constant is k1 and k minus 1. Okay, k1 is for forward reaction and k minus 1 is for backward reaction. So at the initial condition, it will be a, b and c, d. Okay, so at time t, when time is t, it will be a minus x and b minus x. It will be c plus x and d plus x. Okay, now net rate of reaction will be dx dt is equal to rate constant for forward reaction k1 and a minus x, b minus x, minus rate constant for backward reaction k minus 1, c plus x, d plus x. Okay, now I will divide this whole equation by k minus 1. Okay, this is k minus 1. dx by dt is equal to k1 by k minus 1, a minus x, b minus x, minus c plus x, d plus x. Okay, here I will write capital K instead of k1 by, here capital K is equal to k1 by k minus 1. Next I will divide this whole equation by k minus 1. So it will be 1 by k minus 1 dx dt x square minus k a plus b c plus d by k minus 1 x plus k a b minus c d by k minus 1. Okay, so next it will be, I will consider this part. as L, capital L, and x plus this whole part I will consider this is M. If you evaluate the solution of this equation, that means x, you will get two solution. One is L minus L square minus 4m by 2, and another one is L plus L square minus 4m by 2. Okay, so if these two are two solution, then we can write here k minus 1 dx dt is equal to x minus L square by 4m by 2 multiplied by x minus L plus L square minus 4m by 2. Okay, if you multiply this two part, then you will get this one, x square minus Lx plus m. So next, x, I will write this huge part as a, and this huge part, here it is minus, here it is plus, so it is different from this one. Okay, so it is x minus b. So I will write dx, this x part will come here, x minus a, x minus b, and this other part will come here, so it will be k minus 1, k minus 1, and you can see that this is k means k1 by k minus 1, and it is multiplied. Okay, so you can write like this, and k minus 1 into 1 is equal to k minus 1, so it will be cancelled out. So you can write k1 minus k minus 1. Okay, so if you integrate this equation, you will get k 1 minus k minus 1 is equal to 1 by t a minus b ln x minus a, x minus b, it will be b, and here it is a. So it is also easy to remember. Here it is a minus, it is almost equal to similar to first order reaction, where k is equal to 1 by t ln a by a minus x. So here it is something little bit different. Here it is a minus b. So if you write a is coming first, so I will write in the upper part x minus a, b is coming after a in the second time, so I will write here b minus x minus b. So as I have written here a, so it will be opposite of a, it will be b, and it will be a. Okay, so I am just saying this for to memorize or remember easily. Okay, so this is the final equation for rate constant, equation for reversible reaction, where the two opposing processes, that means forward reaction and backward reaction, possesses second order, that means a plus b and c plus d. So for those reaction, reversible reaction, this is the general equation. Okay, now for better understanding all of this, let's solve a problem. So in this question, there saying that find out the value of rate constant for forward direction and rate constant for backward direction. This is the reaction, and this data is given. Concentration of reactant at the initial state. This is the concentration. This is the concentration of reactant when it is equilibrium. Reaction is equilibrium state, and this is 10. That means time. When time is 10 second or something, then at that moment concentration of reactant is this one. Okay, so for this question, first of all we have to write the reversible reaction Kf Kb. So from this reversible reaction we can write Kf at the equilibrium state. At equilibrium, what we can write Kf, that constant for forward reaction, and concentration of reactant A minus Xe at equilibrium, and it is equal to rate constant for backward reaction and concentration of reproduct, which is Xe. Okay, so from this we can write A minus Xe by Xe is equal to Kb by Kf. Okay, now Kb by it will be Kf. We will invert this, and it will be Xe by A minus Xe. Okay, next we will put the values. This is the values for Xe value 0.172 by A means the initial concentration for reactant, this one 0.30 minus Xe again 0.172, which is equal to 1.343. For this question we have to remember one equation, which is we have A by A minus Xe Kf T is equal to ln A minus Xe by Xt minus Xe. I will put the values. A means 0.30 minus Xe, that means this one 0.172 Kf. We will find out Kf, and time is 10. In the equation it is given A, concentration of A 10, that means time 10 second. So we will write 10 is equal to ln A means 0.30 minus Xe 0.172, and Xt, when time is 10 the concentration is given in the question, which is 0.285 minus 0.172. Okay, next this 0.30 by 0.128 Kf 10 ln 0.128 0.113. Next 2.343 Kf 10 is equal to ln 1.132, which is equal to 0.123, and from this we can calculate Kf. Kf is equal to 0.123 divided by 2.343 into 10 is equal to 0.123 by 23.43, which is equal to 5.25 into 10 to the power minus 3. As we have already calculated, kf by kb is equal to 1.343, which is k equilibrium. Okay, so as I have calculated kf, this one kf is calculated, so from this equation we can calculate kb. Okay, kf by kb is equal to 5.25 into 10 to the power minus 3 by kb is equal to 1.343. So kb is equal to 5.25 into 10 to the power minus 3 divided by 1.343 is equal to 3.9 into 10 to the power minus 3 second inverse. Okay, let's discuss about principle of microscopic reversibility. So this principle says that in a reversible reaction, the rate constant for forward direction and backward direction are equal when it is in equilibrium. So the principle that for one step elementary reaction at equilibrium, the rate of forward reaction is equal to the rate of backward reaction is known as the principle of microscopic reversibility. This principle helps us in establishing the connection between the equilibrium constant of an elementary reaction and the rate constant of its forward and backward direction. That means in a reversible reaction, there are some elementary reaction processes through which the reaction proceed. Okay, so on those elementary processes also follows the principle of microscopic reversibility. On those elementary processes also, the forward rate of forward is equal to rate of backward direction. Okay, thank you so much for watching this video. If you like it, please subscribe my channel and share with your friends.